Okay, we'll start on chapter 16. We'll talk about electric charge and electric field, shifting gears from chapter 15 a little bit. I'll be able to answer why this comb is able to retract those pieces of paper. So I'll introduce the type of charge that we can have associated with static electricity, positive charge, negative charge, and how charge must be conserved. We'll see these positive and negative charge inside of an atom and talk about insulators and conductors. We'll talk about how we can induce charge and forces that are related to charges. There's some vector nature that we'll kind of revisit, and then we'll talk about an electric field lines and how that's related to conductors, and lastly just some kind of basic applications, photocopier machines, so on and so forth. And another important concept is going to be Gauss's law. Now, static electricity is something that can be generated by rubbing two objects together. We can think about rubbing a plastic ruler with some silk, and it will tend to attract some paper. We can also say, hey, I know if I run a comb through my hair, it's going to hear the zap, zap, zap of static electricity. Could be my fleece jacket rubbing up against my car seat, or pulling objects out of the clothes dryer. There's going to be some static electricity associated with that. Now, scientists of old, what they essentially were trying to figure out is, how does static electricity come? How many flavors does it come in? And essentially it comes in two different flavors. It's going to come in positive and negative. Now you can kind of picture some evil scientists rubbing some plastic, or back in the day it would be amber, rod with some silk, or with some fur. Then what's going to happen is there's going to be a net negative charge picked up by the plastic ruler. If you had two of those guys, you suspend this guy by a string, there's going to be some force of repulsion. So two negatively charged plastic rulers are going to repel. Similarly, if you rubbed glass with fur, then it's going to get a net positive charge. Do the same experiment, and there's going to be some repulsion. So we found that like charges are going to repel. However, if we did that with a plastic or amber rod and brought in our glass rod, then there's going to be a force of attraction. And so opposite charges are going to attract. So negatives are going to repel negatives, positives are going to repel positives, and negatives and positives are going to attract each other. Now, one thing to kind of keep in mind when it comes to electrical charge is that it's going to be one of these conserved quantities that I keep on rambling on about. Suppose I've got my glass rod and I rub it with my silk, then what's going to happen is the glass rod's going to have a net positive charge. The silk rod has to have an equally net negative charge. So we can't create or destroy charge, we can only separate them. Now we do have to introduce just a little bit of chemistry. Again, I'm not a chemist, so I don't care too much about the chemistry. I care about the charges within the atom. So the electrical charge distribution inside of the atom is going to consist of a small massive nucleus which has protons and neutrons in there. Protons have a net positive charge, so we're going to have this very, very, very tiny nucleus with a net positive charge. Atoms are neutral in charge, and so there has to be some negative charges associated with an atom. It's kind of carried by these electrons. The electrons have the same amount of charge, only it's going to be negative, and they kind of orbit this proton, kind of like satellites orbiting a sun. One thing to kind of keep in mind when we start talking about electricity is that these electrons, kind of a symbol right there, are going to be much, much, much easier to rip off of an atom than it is going to be to try to yank a proton off. If we change the protons, we're actually talking about nuclear reactions. If we rip an electron off to carry some charge for us, then we've simply created an ion out of this atom. So these electrons are going to be the thing that's free to move. And just kind of to have it in writing here, atoms are going to be electrically neutral, since protons and neutrons have the same, or protons and electrons have the same amount of charge. There's going to be the same number of protons as there are electrons, so same charge, positive charge and negative charge. So the typical atom is going to be neutral. And what we're doing is when we charge an object, all we're really doing is we're moving electrons from those orbits, especially the outer orbits, from one object to the other. Charge itself, number of electrons, is going to be conserved. Now if we were to combine some atoms, where we would have what we would call a molecule, and some molecules, most molecules are also going to be net neutral. You're going to have the same number of positive as an A and negative. However, charge doesn't have to necessarily be distributed evenly throughout a molecule. Take, for example, water, H2O, so 2 hydrogens and 1 oxygen. This is what we call a polar molecule because it has 2 electrons and 2 protons, so it's going to be net neutral. However, there's some preferential separation of the charges such that there's more negative here than there is positive here, and so we have what we call a polarized molecule. We could also say this is going to be a dipole, simply meaning that there's going to be some separation of negative and positive. So we can talk briefly about different types of materials now and how they interact with charge. There's going to be 2 types. There's going to be insulators and conductors. For conductor, there's going to be the ability for charge to flow freely over this material. Essentially, you can kind of think of metals as having free electrons that they're willing to give up, so charge is going to flow. If we have 2 spheres down here, 2 metal spheres, this one's initially charged with, say, 6 positive charges, and we have a neutral sphere over here. If we put a metal across these guys, then the charge will tend to flow and equalize out. An insulator is not going to let any charge flow. Pretty much anything that's not a metal is going to be an insulator. So we can kind of think of wood. Wood doesn't have all the free electrons that metals do, and so essentially it's not going to allow the it's not going to allow the electrons to flow from one of these spheres to the other sphere. Some materials are going to be semiconductors, and they're going to behave either as a conductor or as an insulator depending on, say, their temperature. You're not necessarily worried about those so much in this class. Now we know that we can we can get charges by rubbing things. What happens if we were to touch 2 metal objects? That's going to allow us to slosh charge around through conduction. Remember, conduction we talked about in a thermal sense that there was going to be some touch. So if I bring in a rod that has some net positive charge and I touch it with this guy, then this originally neutral rod is going to start to acquire a positive charge, and this one's going to end up at the end of the day with less positive on it. That little arrow right here, what that's kind of saying is that this is going to be the direction that the electrons are going to be flowing. Remember, electrons are what carry the charge. So the electrons are hopping off of this guy onto this guy, leaving this guy with a less net negative positive charge, and this guy is going to gain a net positive charge. So keyword for conduction is going to be touch or contact. We can also charge things, or charge metal rods, through induction, which is going to be kind of the same, but there's going to be no touching required for induction to happen. Suppose I have an initially neutral rod and I hook it up to this little symbol over here, which is going to be the symbol for a ground. Essentially that's going to be a reservoir for electrons. If I bring in a negatively charged rod over here, then these negatively charged electrons are going to attract the positive charges over here. They're also going to repel the negative charges, so these negative charges are going to essentially flee down through the ground, through their escape path. Now suppose I go ahead and I cut the wire to the ground, and I can pull away my negatively charged rod, and I'm left with just a positively charged rod that was charged through what we call induction. Now what happens if we have a non-conductor or an insulator? Suppose I have a glass rod, or a rod with some charge in it, and I bring it near a non-conductor. It won't be charged if I touch it, and it won't be charged through induction, but it can actually experience some charge separation. So suppose I have a charged rod and I have my non-conductor right here. It's got the positive charges and some negative charges kind of all scattered around it. Then if I bring this rod in real close, then what's going to happen is it's going to push the positive charges in that direction. It's going to pull the negative charges in that direction. So I can kind of end up with, my negative charges over here, my positive charges over here, and I end up with a polarized atom. The reason I've polarized it is because I've brought in this outside stimulus, and that's going to be true for pretty much all of the molecules that are inside of this non-conducting rod over here. And this non-conducting rod is going to have some net polarization associated with it. And really, this is kind of the thing where you see if you take a balloon and you rub it against your hair, say you're giving that balloon kind of a net positive charge. And what you can do is you can bring that balloon up to a non-conducting wall. Drywall doesn't conduct. It's going to polarize, and it's going to be able to still be attracted to the wall. This is also why the bits of paper attract to the positively charged comb on the very first slide. So let's introduce really quickly something called an electroscope, which is going to be something that can detect charge and actually tell us what type of charge is actually we're playing with. So here we kind of have some metal, and it goes through an insulating ring, and this is just some metal that holds a piece of glass that we can look through. And this metal right here is attached to two very thin, lightweight gold leafs that can freely move. And what we can kind of do is we can charge this guy through an induction or conduction, where suppose we bring in some positively charged rod, it's going to pull the negative charges up here, and we're going to be left with some negative, or the positive charges down there. And these gold leafs are going to say, hey, wait, I have a positive charge, I have a positive charge. There's going to be a net force of repulsion. You're going to see the leaves kind of separate out. We could also say, hey, I'm going to touch it right here and spread positive all throughout this conductor. Because it's a conductor, the charges are going to separate, and I'm going to have two positively charged leaves that feel a force of repulsion away from each other. We can then use this electroscope to say, hey, what type of charge do I have on my rod? Suppose I have a net negatively charged electroscope. So here I have a negative charge, like charge is going to repel. Suppose I go ahead and I bring in a negatively charged rod. Then what that rod is going to do is it's going to say, it's going to push all these negative charges as far away from that rod as possible, because there's a force of repulsion, and these leaves are going to have more charge on them. They're going to be pushed further apart. Similarly, if I bring in a positively charged rod, then it's going to draw up those electrons to this end, so there's not as much negative down here, and so this spread is going to be larger. So I can kind of figure out what charge is on the